March. Okay, and I plan to include all the chapter 13 sessions in the first test. I will send you a formal announcement to Canvas. But what I want to say is, so there are two parts of calculus: derivatives and integrals, right? The derivatives, as you probably have already seen, is not very challenging. There are not so many things to remember. So as long as you practice them, you get the principle of taking partial derivatives. Conceptually, it is less challenging comparing to integrals. However, still, I find people in the end struggle to get points from these questions. Okay. One of the most important things is to remember the difference between the vectors and the scalars. Okay, so this is what we're going to talk about today. 13.6. Okay, so here's the point. In a test, in a final, they're not going to give you a function for just to compute partial derivatives. Right? It's just too simple. Everybody knows how to compute partial derivatives as long as you finish the single variable calculus. However, we do want to learn what is partial derivatives or tangents. Right? This is what I promised you when we first began our chapter 13 discussion. So the partial derivatives, I already mentioned one of the connections between the derivative rate of change and the graph. Do you remember that? For instance, if a function z is equal to f of x, z is equal to f of x and y, and the graph is a surface in 3D. Right, we have a base point. Sticking upwards, you're getting a point on the surface. So this is where you evaluate f of AB. So we can compute the partial derivative with respect to x at its point. We can also compute the partial derivative with respect to y at its point. I mentioned what they are saying in the geometry. Still remember that? Right. Fundamentally, both of them are talking about a rate of change. When you change the point, the base point AB, for a little, the function value will change. Right. So you're taking the portion change of the dependent variable over change of the independent variables. Right. So this is basically a rate of change, and these ones are the limit of the rate of change. In other words, they're talking about the slopes of tangent lengths. Remember that? Right? So that's the close connection between the partial derivatives with respect to the graph, the geometry. As I said, they're not going to give you simple questions for the compute of partial derivatives alone. They want you to take the partial derivative and then be able to tell what these information are going to be put into the geometry. Now with me? Okay, so the partial derivative with respect to x is where I move x little bit. So this is x-axis, this is the y-axis. So a plus h, b is still the same value. So I move in the x direction, change the independent variable x from a to a plus h. So accordingly, my point on the surface will be moved slightly, right? Therefore, the function value will be changed from fab to fa plus hb, right? So this guy is equal to the limit of h goes to 0, change in the independent variables, which is just h, right? Its y is stay put, x is changed by h, and the change in the dependent variable, h plus hb minus of ab. Okay, so this is the definition of the partial derivative with respect to x. Similarly, you can define partial derivative with respect to y. First of all, I want you to understand this is about a rate of change. Second, it is about the slope of the tangent line if you cut through the surface by a plane which is parallel to xz point. So if you have a plane cutting through this surface, which is containing this line right here, right? It will cut through the surface into a curve, and then you compute the slope of the tangent line at this point. This is exactly the partial derivative right here, right? So the partial derivative is the rate of change, and also it is the slope of the tangent line which is the intersection of a plane with the surface. You can also interpret partial derivative with respect to y in a similar way. And also, I propose the question. So from this base point AB, I can move in the x direction by h. I can move in the y direction by h. I can, in fact, move in all possible directions on the plane by h. All right? So if I want to specify the direction where I'm moving the base point AB, I have to have a vector u, which is on xy plane. All right? So I'm moving in the xy plane, so I have to have a direction which I'm moving towards. Okay? So for instance, if my direction is in the x direction, u is in the same direction as I. All right? So this is exactly saying if I move in the x direction. And if I make my directional vector to be the unit vector of y-axis, I'm actually moving in the y direction. Are with me? Okay? So generally, I can specify any directional vector u here, which is given by two components, u1 and u2. So in the case of x-axis, which is equal to 1, 0. In the case of y-axis, it is equal to 0, 1. So given any unit vector u on the xy plane, I can have a direction which is in the direction of u, and then I will be able to move this base point in this direction by small amount. All right? So I move in this direction by small amount, the function value will also be changed by a small amount. Are you with me? So I have a change in the dependent variables and a change in the independent variables. So I can take a rate of change with respect to this direction. So I can define so-called directional derivative. So this directional derivative is basically a rate of change. Which is also equal to change in z over change in xy in the u direction. Okay? So the definition is this is equal to limit h goes to 0, f of a plus h u1 b plus h u2 minus f of ab divided by h. Okay? So basically what it means is if I move in h direction, in the u direction by h, then originally my point is AB. After you move, this point is going to be A plus h u1, B plus h u2. Okay? Are you convinced yet? I'm going to say it again. If I have a directional vector u, and I move in this direction by h amount, then my x will be changed by h times the x component of u, and y will be changed by h times the y component of u. All right? So in a very, very special case, if u is in the x direction, u1 is equal to 1, u2 is equal to 0, you're getting exactly a plus h and b. Yes? If it is in very special case, u is in the direction of y-axis, u1 is 0, u2 is 1. So x is still a, y is going to be changed to b plus h. All right? So now here is my movement. I'm sitting on AB. If I'm moving in x direction, I have a rate of change. That is given by the partial derivative with respect to x. If I'm moving in the y direction, I'm getting a partial derivative with respect to y. If I'm moving in the u direction, I'm getting a directional derivative with respect to this direction. Okay? So in a special case, I can in fact say the following. If the directional derivative u is equal to I, which is the unit vector in x direction, this is exactly equal to f sub x. Right? And directional derivative with respect to the y direction, this is exactly equal to s sub y. So these are very special directions. Okay? But you can define this rate of change in any after direction on xy plane. Okay, here is really the key part I wanted to stress. I will say this again, partial derivatives are easy to compute, but a lot of people got confused in the end. Here we are having several different objects. First one is this U vector. U is always a vector on R2, so U has two components. And because it is only talking about the direction, so we want this vector to be of unit length. U is a unit vector in R2, or more strictly speaking, xy plane. And the directional derivatives, is it a vector or is it a scalar? Directional derivative, is it a scalar or it is a vector?
Scalar.
What is the keyword in the sequence of equations? If it is talking about a rate, it has to be a number. So this is a scalar. So a lot of people get confused in the end, not because they don't know how to compute partial derivatives, they just do not know what they are computing. So the directional vector is a vector, but directional derivative as a rate of change is always a scalar. Okay, so this is extremely important. If I want to compute a directional derivative for a particular vector, I'm always getting a number or a function in the end. Right? I'm not getting a vector, so this is extremely important. A lot of people get in the end, they lose point because they simple fact. Okay. Next, I'm gonna make this as a formula. So I already have the definition of the directional derivative, and I also have a formula of how to compute it. It is exactly equal to f sub x, f sub y, dot product with u1, u2. Or it is equal to u1 multiplied by partial f partial x plus u2 multiplied by partial f partial y. Okay? So again, I have a directional vector which is given by u, and they have two components, u1 and u2. This directional vector can be very arbitrary on the xy plane. Especially if I have u equals I get an f sub x. I got a u equals j, I'm getting a f sub y. So special case, you have these two partial derivatives. However, even they are very special, they will be sufficient to generate all the directional derivatives. Okay? For any arbitrary directional derivative, it is always equal to a linear combination of these two partial derivatives. And these linear combinations are exactly the x component of the vector multiplied by partial derivative of x, and y component of the u multiplied by the partial derivative with respect to y. Okay? So even fx and fy are both special directional derivatives, but any other general directional derivative is always a linear combination of these two. Okay? So this is the formula of computing the directional derivative. You have a function, right? If I want to compute the directional derivative for a given vector u, I'm computing the partial derivatives with respect to x and y, and then I do a linear combination of them. Okay? Now with me? So now I want to practice quickly how we can do this. So if I have fxy is equal to 5 plus 5x squared minus y squared, and this u is equal to 1 over square root of 2, 1 over square root of 2. I want to compute the partial derivative of u and f. And also I want to compute the partial derivative of u, partial directional derivative of f in the direction to u, evaluated as 1 minus 1. Okay? So this is what we can compute. In the very beginning, I have to make sure the directional derivative is indeed a unit vector. Okay? I will tell you it's a unit vector. X component squared plus y component squared is equal to 1. All right? So this is indeed a unit vector. And then the way of computing the directional derivative of f with respect to u, no matter what I compute in here, in the end, I'm supposed to get a scalar function, right? If I'm evaluating at a given point, 1 minus 1, in the end, I'm getting a number,
Okay.
right? You're getting a number, right? So directional derivative is about a rate. This is how you remember it. It is a rate of change, so it has to be a number. Vector is not talking about a rate, right? A rate is a number. So the linear combination of this guy is equal to 1 over square root of 2 multiplied by the partial derivative with respect to x. What do you got? 10x. We have been practicing this for 2 weeks already. And then 1 square root of 2, 1 over square root of 2 multiplied by minus 2, 1. So in the end, I'm getting a 5 square root of 2x minus square root of 2, 1. So this is going to be my directional derivative. Okay, this is the directional derivative. It is indeed a scalar value function, right? You plug in x, y, you're getting a number. So particularly, if I write a duf evaluated 1 minus 1, what am I getting? So it's going to be 5 square root of 2 multiplied by 1 minus square root of 2 multiplied by minus 1. So in the end, I'm getting a 6 square root of 2. Okay? Am I clear? So this is how you compute it. Again, we can plug in this number into the geometry, into the graph, and explain what the 6 square root of 2 means. Right? So if you have a function in this form, you have a surface. If you have a surface, you can cut through the surface by different planes. If you cut through the surface by a plane parallel to x-axis, and then you got a curve over there, you compute the slope, you're getting a number. However, here we're talking about directional derivative with respect to u, so we have to cut through the plane by we have to cut through the surface by a plane parallel to this vector, right? So you will cut through the surface into a different surface, different curve, I'm sorry. So for instance, if this is the plane, you will have a surface, the intersection, and this is the curve. So at a given point of 1 minus 1, you compute the slope of this tangent line to this curve, that is exactly going to be 6 square root of 2. Okay? My picture is not very precise, but you got a picture. Okay? So roughly speaking, these different directional derivatives are talking about slopes of different tangent lines of different curves.